The speaker is Melissa Lee, who is advertised as an international plenary, which is technically true, but of course she is from Perth. She did her, I looked back this morning, it was 2011 when I first saw her smiling face in one of my classes. And she went on and did a master's here with John and Michael, and then a PhD at Imperial with Martin Liebeck, and is now at the University of Auckland, where she's going to present us with an algebraic tasting platter. Take it away.
Thanks, Gordon. And I'd like to thank the organisers of the conference for not only inviting me to give this talk, but for organising what I judge to be a very successful online conference. All right, so as you can see, my talk is entitled An Algebraic Tasting Platter. And my motivation for this talk is that ever since I started my postdoc about a year and a half ago now, I've kind of been going a little bit overboard with the sheer number of mathematical problems I've been getting interested in. And so I wanted to tell you about some of them. So some of them I've done quite a bit of work on, some of them are works in progress, and for the vast majority of them, I'll have some open questions, which I hope will be something for you to nibble on. So, okay, let's get going. Here's the menu for today. So we're going to start with my old favorite topic, bases of permutation groups. And then I'll be moving on to IBIS groups, which are a certain type of groups where the bases all have a very strong property, which I'll discuss when I get to them. And then we'll be looking at Saxel graphs, which are a sort of graph that you can define using permutation groups with a particular base size. Then for dessert, we'll be looking at prime graphs of finite groups. And then finally, with your coffee, I'll be talking about some extremely primitive groups. Okay, so every tasting platter needs a good foundation. And for us, that foundation is a base. So what is a base? Well, if we have a permutation group G acting on a set omega, then a base for G is a subset B of omega such that the pointwise stabilizer of B in G is true. So if we take a moment to think about the sorts of bases that we can have, well, first of all, the whole of the set omega forms a base for G because we're assuming that G is a subgroup of sim omega, so it's faithful, and so the only element, the only permutation in G that can fix every element of omega is going to be the identity permutation. Now, bases have in the past had applications since the early days of permutation group theory, where they were used to give upper bounds for the orders of groups with particular properties. And they also have uses in computational group theory. And so for these applications, we're usually interested in the size of the smallest base for G on omega, which we call the base size, and we denote it by this B of G here. Right, so let's see some examples of base sizes. Well, first of all, if we take G to be the symmetric group, Sn, acting naturally on n points, then the base size here is n minus 1, because if we had a smaller base, so then we would have at least 2 elements, 2 points outside our base, then you could take the transposition that swaps those two, and then you would have a permutation which fixes your supposed base, so your base can't have been a base at all. So we need at least n minus 1 points in the base, and in fact, n minus 1 is the base size. On the other hand, if we take any finite group G acting on itself by right multiplication, then it's pretty easy to see that the base size is equal to 1, okay? Now, in some sense, these two examples are on opposite extremes, because on the one hand, we have the symmetric group here, where the base size is only 1 less than the degree of the action. Okay, so it's very, very close to the degree of the action. And on the other extreme, we have this action where you could take an extremely large group G, but whatever group you take, the base size is always going to be equal to 1. Oh, and when the base size is actually equal to 1, then we say that G has a regular orbit on omega. Okay, so we've kind of got two extremes here. Now, before I go on, I should say that in the rest of my talk, I'll be assuming that my groups have finite order and also that my actions are faithful. Okay, so that means that I can't have 2 permutations which act in the same way on the entire set. Right. Okay, so how do we get a feel for what the base sizes of permutation groups can be, how big or small? Well, here is an easy lower bound on the base size for an arbitrary permutation group. So if you've got a group acting on a set of size n, then the base size is at least log of the size of the group over log n, okay? Now it turns out that, well, not always, but in many important cases, this lower bound is actually a pretty good estimate of the true base size. And in many cases, it's actually equal to the base size. Now, this is a very easy little lemma to prove. So I'm going to give you the proof here. So by definition of a base, we know that the pointwise stabilizer of a given base B is trivial, okay? And what that means is that each element of your group is determined by how it acts on a base, okay? Because if I had two elements of the group, say G and H, which acted in the same way on the base, then I would have, if I compose G with H inverse, I would have something non-trivial which fixes the base, okay? And that's a contradiction. So we know that each element of the group is determined by how it acts on a base. And so actually the size of the group is bounded above by the number of base images of the base. And so the number of base images is, well, I suppose less than this. So the degree to the size of the known base. And since this argument holds for all bases, it in particular holds for the smallest one. So that's how we get this expression here. And then if you take log of both sides and rearrange, you get the desired result. Okay, so that's a lower bound for the base size. Now, as I said earlier, there are applications of bases to computational group theory, and we're usually interested in the smallest base that we can get for an arbitrary permutation group there, and we're also interested in generally having small bases. So I guess the next question is, how easy is it to find small bases? And also, is it even possible to find small bases for arbitrary permutation groups? And the answer is not really. So Pieper showed in 1993 that there exists a universal constant C greater than 0, such that almost all subgroups of Sn have their base size strictly larger than C times n. Okay, and by almost all here, I mean a proportion tending to 1 as this n tends to infinity. Now, okay, so that means that we can't find any good, and here good means sublinear, upper bounds for the base size that hold for arbitrary permutation groups G. Okay, but being the tenacious mathematicians we are, we instead of giving up, we're going to just restrict our focus to a certain class of groups, and a class of groups that has a lot of attention in the literature are the primitive groups. Okay, so recall from previous talks that a group is said to be primitive if it acts transitively and also doesn't preserve any non-trivial partitions of the set that we're acting on. Now, the primitive groups are classified by the Onan-Scott theorem into one of these 5 types. So we've got almost simple groups, product type groups, twisted reed type groups, diagonal type, and affine type. And I just want to talk a little bit about base sizes for almost simple groups. Okay, so this first collection here. Right, so recall that we say that a group is almost simple if we can find a non-abelian finite simple group S such that our group G is contained between S and its automorphism group. And in this case, S is called the socle of G. Okay. Now, I need to distinguish between 2 further sorts of actions. So if you've got an almost simple group with socle G0, then we say that a transitive action of G on omega is standard if it falls into one of the following 2 cases. So either you've got a classical group acting on an orbit of subspaces of its natural module. So here, this kind of vaguish description encompasses a couple of other cases. For example, if you've got a classical group acting on an orbit of subspaces of complementary dimension, and there's one other case, but roughly it's classical groups acting on an orbit of subspaces. So if the action is either that, or if the socle is the alternating group and your omega is an orbit of the K subsets or partitions of 1 up to n, then we say that the action is standard. And otherwise, we say that the action is non-standard. Okay. Now, in the 1990s, Cameron and Cantor conjectured that if you have a primitive almost simple group, okay, that is acting in a non-standard way, then the base size should be bounded above by a constant. Okay, so no matter how big the group is, or how large the degree of the action is, we should be able to bound the base size above by a fixed constant. Now, this was proved by Liebeck and Shalev in 1999, where they showed that such a constant exists. But it wasn't until later that this constant was actually established. And it was established by these people for the different types of socles. So let's have a look what it says here. So of course, since the socle is a simple group, we can appeal to the classification of finite simple groups. And so it was proved that if the socle of your almost simple group is sporadic or exceptional of Lie type, then the base size is at most 7. And the only time where we have equality here is if G is equal to the Mathieu group M24, acting naturally on 24 points. If instead the socle is alternating, then the base size is at most 5. This is, of course, supposing that we're in a non-standard action. And finally, if the socle is a classical group, and again, the action of the group is non-standard, then the base size is at most 5. Now, something else that I want to point out just before we go on, because it will be important later in the IBIS group section, is the way that these results were actually presented. So for the sporadic and alternating groups, the statement of the results was quite a bit stronger than just this upper bound on the base size. The authors of the papers actually had a result which said either the base size is equal to 2 for these groups, or here's a list of groups where the base size is strictly larger than 2. Okay, and we'll see why in a couple of slides. We'll see why 2 is the smallest interesting base size. And so really, in these papers, the groups were actually, the base sizes of these groups were actually fully determined. Whereas for the groups of Lie type, the results were more of the flavor, like, the base size is at most 4, and here are a couple of exceptions and so on. Okay, so that will become important in a few slides' time. So this is all about almost simple groups, almost simple primitive groups. What can we say in general for primitive groups? Well, Dion, Halassi, and Marotti in 2016 showed that if you have an arbitrary primitive permutation group of degree n, then the base size is bounded above by 45 times this ratio of logs that we saw in that lower bound earlier, plus some additive constant c. Okay, and their result settled a conjecture of Pieber from the 1990s that a lot of people had done work on in the intervening 30 years. And then more recently, actually during the course of my PhD, Halassi, Liebeck, and Marotti, so Martin Liebeck was my PhD supervisor, they showed that the base size actually can be bounded above by 2 times this ratio of logs plus 24. Okay, so this is quite an improvement here. And the authors note that this upper bound multiplicative constant of 2 is optimal. And the example that they give is if you have the symplectic group acting on its natural module, then that roughly meets the upper bound here. But they do say that this 24 could be improved upon potentially. Alrighty, so now we've kind of had a look at this family of primitive groups, and we've seen some upper bounds on the base sizes that hold for the entire family. What happens if we go about this the other way? So what happens if we say, okay, let's require that the base size is equal to C for some C. What can we say about the sorts of groups that have base size exactly C? All right, well, we might as well start from the bottom. So if the base size is equal to 1, so the group has a regular orbit, then since we're looking at primitive groups and primitive groups have maximal point stabilizers, that must mean that the group we started with is cyclic of order P. Okay, so that's not very interesting. So as I mentioned earlier, the smallest interesting base size is 2. And in fact, I believe it was in the 1990s, Jan Saxel proposed a program where we should try to classify all primitive groups with base size equal to 2. And lots of work has been done on this by many people, including myself, but this is still wide open. Okay, so as far as I know, all of the groups with base size 2 have not been classified for each of the in each of the 5 types according to the Jan-Scott theorem. So there's still a lot to do there, even though much progress has been made. And then, of course, you could ask a more general question, which is, can we classify the primitive groups with the base size equal to C for some C? And maybe a little bit counterintuitively, there's been some complete classification results here in specific cases. So I believe, for example, Tim Burness has classified all of the almost simple primitive groups where the base size is equal to 6, for example. Okay, so there's lots to do here. Right, so now it's time to move on to our next problem, which is IBIS groups. So I've got a little picture of an IBIS here. Right, so now we're going to talk about ordered bases. Okay, so we say that an ordered base, B1 up to BT for a finite group, is irredundant if, as I stabilize progressive base points, I always get a subgroup of the preceding stabilizer. Okay, so I can get a stabilizer chain here where each of these inclusions is strict. Okay, right, well then we say that G is an irredundant bases of invariant sizes group, or an IBIS group. Okay, I get the feeling they chose this name for the acronym. Anyway, if all of its irredundant bases are of the same size. Okay, so as you imagine, this is an extremely strong condition. And Cameron and von der Flas showed in 1995 that actually G being IBIS gives you a little bit more. So if you've got an IBIS group, then all irredundant bases for G are preserved by reordering. So if you have an irredundant base for G, you can reorder it and you get another irredundant base. And also, all irredundant bases for G are bases of a matroid. Okay. Right. Well, I think as someone said earlier, we're mathematicians, we like to classify things. So there's this problem to classify the IBIS group. So you would think that this would be maybe not easy, but achievable, considering this is such a strong definition. But actually, Peter Cameron, in some notes that I found, says that this seems to be a completely intractable problem. Like he would be surprised if there was any hope of classifying the IBIS groups in general. So maybe we can reduce down to a hopefully slightly easier problem, which is to classify the primitive IBIS groups. Now, in a very recent paper by Lucchini, Morigi, and Moschiatello, they showed that if G is a primitive IBIS group, then G has to be one of either affine type, almost simple, or diagonal type. Okay, and further to that, they actually classified all of the primitive diagonal type IBIS groups. So if you've got a primitive IBIS group of diagonal type, then it's a member of this family here. Okay. Rightio. Well, that leaves us with these two other cases to deal with. And I've been having a look recently at the almost simple groups. Okay, so what can we say here? Well, in their paper, Lucchini et al. Have this really nice lemma, which says that there are no primitive IBIS groups with non-abelian socle and base size 2. Okay. Now this is where we go back to the classification of the base sizes for almost simple groups that we saw in the last section. So Burness et al. Showed that if the socle of the almost simple group is either sporadic or alternating, and the base size is strictly larger than 2, then we know exactly what those groups are. Okay, we know their base size. So what I've basically done, excuse me, in the past few weeks is actually just check all of them to see which ones are IBIS. Okay, and as you might expect, a considerably small number of them are IBIS. So here are the lists. So this is the list here for the sporadic group. So here I've got the group, the point stabilizer, and then what the base size is. Okay. And something that you'll notice is that these kind of split naturally into two families. Okay, so we've got M24 down to M23, down to M22, and so on, and the same thing happening here. And actually, if you refer to the paper where the base sizes, where these groups with base size strictly larger than 2 are given, there are over 200 examples. Okay, so it's kind of amazing that only these 5 are IBIS. Okay. Now, for the alternating and symmetric groups, the groups with base size strictly larger than 2, there's a couple of infinite families that you can show are not IBIS, and then there's probably a dozen exceptions, like exceptional cases. So here, actually, I would say roughly half of those appear in this table here. Okay, right. So, I mean, where to go from here? So of course we need to look at the groups of Lie type, so complete the classification of almost simple primitive IBIS groups. And as I said, it's maybe not so easy because we don't actually even have, as far as I know, a classification of those with base size strictly larger than 2. Okay, and you know, that we haven't even discussed the affine primitive IBIS groups. Okay, so there's again lots to do here. All right, so now on to the third problem, Saxel graphs, which we can think of as the cheese of our tasting platter. So here's the definition, which was originally given by Burness and Giudice in a paper last year. So if you've got a permutation group with base size 2, then we can define the Saxel graph of this permutation group, and it has vertices being the elements of the set you're acting on, omega, with edges between pairs that form a base for G. Okay, let's see an example. So here I've got the dihedral group D8 acting on the square, and I've labeled the corners here, as you can see. Now it's pretty easy to see that if I consider which subsets of these pairs form a base for G, then 1 and 2 form a base for G, but 1, 3 does not, okay, because you can still reflect about this axis here. Okay, so if we think about drawing the Saxel graph, so the vertices will be the points 1, 2, 3, 4, and drawing edges between vertices that form a base for D8, we see that actually the square that I've drawn is a Saxel graph. Okay, and an extra property that we can observe is that the diameter of the Saxel graph is 2. Okay, so the diameter, recall the diameter of a graph is the maximum length of the shortest path between any 2 vertices. Okay, so the longest minimal path here is, for example, between 1 and 3, length 2, so the diameter is equal to 2. Right. So what sort of properties do these Saxel graphs have? Well, Burness and Giudice in their paper showed that if you've got a transitive permutation group with base size 2, then the Saxel graph is connected if G is primitive, that the Saxel graph is regular, so every vertex has the same valency, and that valency is C times the order of H, where H is a point stabilizer, and C is the number of regular orbits of H. So we know that H has regular orbits because we know that G has base size 2. And also they showed that G acts transitively on the vertices of the Saxel graph, okay? And this just follows from the fact that G is transitive on omega in the first place. And in fact, G is isomorphic to a subgroup of the automorphism group of this Saxel graph, okay? Right, now in their paper, they have a really striking conjecture, which I have been calling the common neighbor conjecture. So their conjecture is as follows. If you've got a finite primitive permutation group with base size 2, then every pair of vertices in the Saxel graph of G have a common neighbor. Okay, so let's think about what this means. It's actually a little bit stronger than the graph having diameter 2, okay, because having diameter 2 just means that every pair of non-adjacent vertices have a third, well, you can find a third vertex that is adjacent to each of them, okay? But here we require the same property if the 2 vertices we started off with are adjacent, okay? So we're gonna have a whole bunch of triangles everywhere, okay? So this is a bit stronger. Right, well, what evidence do we have for this conjecture? So in their paper, Burness and Giudice showed that this common neighbor conjecture is true for groups of degree less than 4096. So I believe they did this with the primitive groups packaging in GAP. It's also true for sufficiently large groups of diagonal twisted wreath type. Okay, so these are some, if I recall correctly, these are some asymptotic results. Now, Chen and Du showed that the conjecture also holds for almost simple groups with suckle PSL2Q, and Burness and Giudice also showed that it holds for some almost simple groups with an alternating or sporadic simple group as their socle. And finally, Burness and Huang recently showed that the conjecture also holds for almost simple groups with soluble point stabilizer. Okay, so there's been quite a bit of work in the literature about almost simple groups, and I and my collaborator Tomasz Popiel looked at this from the perspective of affine type groups. So what are the affine type groups? Well, suppose you've got a d-dimensional vector space over the finite field GFQ. Now, we know that both V and GLV act on V, so V acts by translations and GLV acts by linear transformations. And so if we take the semi-direct product of these two groups, we achieve the general affine group, AGLV. Now, a primitive group of affine type is a primitive subgroup of the general affine group, which contains all of the translations. Okay, and so as I mentioned earlier, a lot of work's been done about base sizes of these things. And so although we don't have a complete description, we know about a lot of primitive affine groups that have base size 2. Okay. So the key to our result was the following intriguing little lemma for affine type groups. So the lemma says that the common neighbor conjecture is true for primitive affine type groups if and only if we can write each vector in the vector space as a sum, W1 plus W2. And we need these W1 and W2 to actually lie in regular orbits of H on V. Okay, so if you stabilize one point with this, this affine type group, you end up with H, which is the set of linear transformations there. And so we need W1 and W2 to lie in a regular orbit of H. Okay. So using this little lemma as one of the main tools, we managed to show that if you've got a primitive group of affine type and the point stabilizer, so the bit that comes from linear transformations, it's almost simple. And also the socle of this almost simple group is sporadic. And of course the group has base size 2. Then either the Saxel graph satisfies the common neighbor conjecture, or this point stabilizer here and the vector space you're acting on is one of 3 pairs where the size of the vector space is enormous. The size is larger than 2 to the 44. Okay. So this is in many ways not very satisfying because we did a lot of work to do the 90% of cases that fall into this first bit here, but we can't quite seem to finish these last 3 cases off. So here are the last 3 cases. As I said, you can see that the vector spaces involved are absolutely massive, as are the groups. But in case there's an interested someone in the audience that might consider working on this, there are 2 sufficient conditions that you can show in order to prove the common neighbor conjecture for these 3 outstanding cases. So first of all, it's sufficient to show that the group H acts regularly on half of the vectors in the vector space. Okay, because if we remember what we said about the valency, of each vertex, that would mean that you could find two vertices with valencies more than half of the vector space. And so by the pigeonhole principle, they would have to have a common neighbor. Moreover, you could also use our little lemma that we had a couple of slides ago. So we could show that every vector in the vector space can be written as the sum of exactly two vectors lying in a regular orbit. Now, of course, in terms of open problems here, there's, of course, finishing this off, and overall, there's the rather ambitious problem of resolving the common neighbor conjecture. Okay. Alrighty. So now I believe we'll move a little bit away from bases as we continue on to the dessert of our tasting platter, and that is prime graphs. So again, we've got a finite group, okay? And we define this graph called the prime graph, or Grunberg-Hegel graph of that group. And this graph has vertices, the primes dividing the order of G, okay? And edges between two prime divisors of the order of G if there's an element of order, well, P times R in G. Okay, so let's see some examples. Well, obviously, if you fix a P and take any P group, then the prime graph is just going to be the isolated vertex labeled by P. Instead, if you've got the Mathieu group M11, then this here is the prime graph. And similarly, this is the prime graph of PSL 231. Now, something that you'll notice is that these two graphs here are isomorphic as unlabeled graphs, but they're not isomorphic as labeled graphs, and so we consider them to be different. Okay. Now, a lot of work has been done to try and see if we can characterize groups by their prime graphs. Okay. So we say that a finite group G is recognizable by prime graph if it's the only finite group with that prime graph. Okay. We say that the group is K recognizable by prime graph if there are exactly K groups, H up to isomorphism, that share the same prime graph. Okay, so you can kind of consider recognizable to be equivalent to one recognizable. And then on the other extreme, we've got groups being unrecognizable by prime graph if there are infinitely many groups with the same prime graph. Now, I encourage you to use your immense mathematical powers to try and figure out which graphs of these you think are recognizable, as in there are finitely many groups with the same prime graph. One of these is easy, so obviously you can take any P group and you'll have the same prime graph, so P groups are unrecognizable by prime graph. It actually turns out that M11 only shares its prime graph with PSL 211. Okay, so these groups are too recognizable. And then PSL 231 is actually recognizable by prime graph. Okay, so it's the only finite group with its prime graph. So how the heck are we supposed to prove these things? You know, there are infinitely many finite groups. Maybe you can say something about the composition factors and so on, but still this seems like a very hard problem. Well, in a recent paper by Cameron and Maslova, they actually showed that if a group is K recognizable by a prime graph, then G has to be almost simple with not abelian circle. Okay, so let's think about what this means. It means that if you take any group that's not almost simple and you have a look at its prime graph, you can tell straight away that there are infinitely many groups with the same prime graph. Okay. On the other hand, if you have an almost simple group and you find a single group that's not almost simple and it has the same prime graph, then you can say that that group is unrecognizable. Okay. So again, we end up with a classification problem, namely, can we, for each almost simple group G, determine whether G is recognizable by prime graph? Okay, a lot of work has been done on this actually, and in fact, all but one of the papers I'm going to reference were actually published before this very nice result by Cameron and Maslow. So let's start with the sporadic groups. So Hege in 2003 actually showed that these sporadic groups are recognizable, M11's too recognizable, and these ones unrecognizable. And beyond that, Hege also did quite a lot of analysis of the remaining sporadic groups and actually showed what the structure of the composition factors should be for a group with the same prime graph as the others. And so Hege really, I would say, was key in laying the foundations for the classification for the other sporadic groups. So in 2006, Svarnitsin showed that J4 is recognizable. Okay, and then there was a gap of about 15 years. And then more recently, Kondratiev just kind of blew the problem out of the water by finding quite a nifty technique to classify most of the remaining examples. Okay, and his technique hinged on knowing the character tables, the modular character tables of each of these sporadic groups. And so he had some reasonably straightforward arguments for each one. But unfortunately, he wasn't able to figure out what the answer was for 3 sporadic groups, namely the monster, the baby monster, and Conway 1, because the modular character tables for those are not completely known. So Tomasz Popiel pointed this problem out to me in preparation for a retreat that our research group had on Waiheke Island a few months ago. And so during and after the retreat, we got in contact with some people that were working on these modular character tables, but they weren't comfortable with publishing them. So then we had to think of some other way. And fortunately we did, and using a similar technique to Kondratiev, but with some slight differences with looking over subgroups and so on, we were able to show that the remaining 3 sporadic groups are recognizable by prime graph. Now you'll notice here that I've talked about only simple sporadic groups. The almost simple sporadic groups are not done yet, but in fact, the vast majority of them, because I've been working on it, actually immediately follow from the corresponding result for the relevant simple group. Okay, so hopefully that's something I'll be able to finish off soon. Right. What about other sorts of almost simple groups? So for the Lie type groups, there's a huge bunch of results. So in many cases, people have published partial results that involve proofs for a single group or a very small family of groups. So I've just chosen a few here. In fact, interestingly, this problem is not even completely solved, as far as I know, for PSL 2Q. Okay, so there are some values of Q where we just don't know whether these groups are recognizable by prime graph or not. Okay, and for a couple of the twisted Lie type groups, we do know completely the answer, but this problem is still really, really wide open. Okay, so there's lots of room for progress here.
Lisa, can I ask a very quick question on that table?
Yeah.
In the second column, you have the K. Is it the same K as the subscript, or is that a different K?
Oh no, sorry, it's a different K. It's just a notation clash.
All right. Okay, nice.
All right. Yes. So finally, if you look at the symmetric and alternating groups, there are also a bunch of partial results. One of the more recent and perhaps most comprehensive ones is by Gorshkov et al., who showed that if you have a group with the same prime graph as an alternating or symmetric group, and n is at least 19, then you should be able to find a normal subgroup K such that G mod K is contained between an alternating and symmetric group. And I think there are some restrictions on this T as well. It has to be kind of close to N. And you also need that this, or this should be the order of K, is divisible by at most 1 prime greater than N on 2. Okay. So I've been intrigued by this case in particular recently, and I've been trying to apply the same techniques that Kondratiev did for all of those sporadic groups to finish off these symmetric and alternating groups. And yet again, I've come up with kind of an annoying result. So firstly, I was able to show that the symmetric groups Sn for n at least 5 are unrecognizable by prime graph. Okay, and the proof of that is very straightforward. It follows basically the method of proof that Kondratiev uses. And then I have this annoying thing for the alternating groups, which says that the alternating groups are unrecognizable by prime graph, unless possibly if either both n and n minus 2 are prime, or n minus 1 and n minus 3 are prime. And this has really, really been bugging me for the last few months. So if you know some stuff about alternating groups that I don't know and you want to get in touch, then please do. And hopefully we'll be able to finish off this problem. Okay, so that's classifying groups by recognizability. What sorts of other questions can we ask about these prime graphs? Well, there's a couple more that I could think of off the top of my head. So first of all, which finite graphs can be realized as a prime graph for some finite group G? Okay, so you could consider this problem either with labeled or unlabeled graphs. And in fact, I have a summer research student working on this problem. So hopefully we'll learn some interesting things. And secondly, what's the maximum number of almost simple groups which have the same prime graph? Okay, so in my research, I think I've found 3 almost simple groups that have the same prime graph. And I believe that someone in the literature has conjectured that the maximum number is 5, but this is not known. Okay, right. So now on to the final bit of our tasting platter, which is extremely primitive groups. So a finite non-regular primitive permutation group, which I'm still calling G, is extremely primitive if a pointwise stabilizer, G alpha, acts primitively on the rest of the set. So the set omega, not including alpha. Okay. And in 2007, Mann, Prager, and Sherish showed that if G is extremely primitive, then G is either of affine type or it's almost simple. Okay. And some recent work, well, some work by Burness, Prager, and Sherish, and quite a recent paper by Burness and Thomas actually classify the almost simple extremely primitive groups. Okay. So either the socle and the point stabilizer intersect the socle belongs to one of 5 infinite families, or is one of 21 further examples. Okay. Now here's the list that they have. So you can see here that we've got a couple of families with the alternating groups, a couple with PSL2Q as the socle, and one family where the socle is a symplectic group. Okay, and then we've got all of these other examples. All right, well, tick, we've done the almost simple, extremely primitive groups. What about the affine type extremely primitive groups? So in their paper, Mann, Prager, and Sherish showed that if you have an extremely primitive affine type group, okay, then and your vector space that you're acting on has dimension B and it's over a prime field of order P, then either H, D, and P is one of a known list of examples, okay, or the prime P is equal to 2 and H is almost simple. Okay. And one further thing that they prove is that if you assume Wall's conjecture, so Wall's conjecture is that the number of maximal subgroups for a finite group does not exceed the order of the group, okay, then this bit in part 2 reduces to a list of 3 infinite families or 16 further possibilities, and we call this list S. Okay. Now, I believe about 10 years ago, Wall's conjecture was proven to be false in general, but I think there is still some hope that it's true for almost simple groups. Nevertheless, Burness and Thomas last year showed that no group in this family of groups S is extremely primitive. Okay. So in order to finish this off, we either need to prove Wall's conjecture for almost simple groups, or we need some way of getting around Wall's conjecture. Okay. And Tim Burness and I worked on this problem earlier in the year. And one key observation we made is that if you've got an affine type group and the point stabilizer has a regular orbit on V, then G is not extremely primitive. Okay, and the reason for that is that if H had a regular orbit on V, then that means that your point stabilizer is trivial. And as I had a bunch of slides ago, since primitive groups have maximal point stabilizers, that would mean that H had to be cyclic of order P. Okay, which contradicts our assumption. So what we managed to prove is that there are no further extremely primitive groups. And this was a nice result in that it seemed to be a nice application of work that we'd both done on bases for affine type groups. All right, so our tasting platter is now complete, and that's all I wanted to say. Thank you very much.